Hi. Let's think about an interesting question, I think. Okay. Let's put yourself in the mindset of a chemist a super long time ago. And you always see these pictures of activation energies and people talk about activation energy. But if you think about it, it's really hard to measure activation energies, right? Because by definition almost, it's a very unstable part of this potential energy diagram. So how did people ever figure out what these activation energies were? Okay, the answer is they would do these experiments at different temperatures and measure the rate of the reaction at these different temperatures. And then from that data, they were able to actually calculate what the activation energy should be. So this question addresses that. Let me show you how this works. Okay, the underlying theory or notion was something that was put forth by Arrhenius. So the Arrhenius equation basically says that the rate constant, the K, for a chemical reaction is equal to some constant multiplied by e to the minus activation energy over RT. So the point is that this kinetic rate constant is a function of temperature. So now if I just rearrange this a little bit and take the natural log of both sides and say that the natural log of K is equal to the natural log of K minus activation energy over RT. And if I just write this a little bit differently again, natural log of K equals natural log of A minus activation energy over R times 1 over T. And the reason I'm writing it like this is to make it look more like a straight line. So this is my y-axis, and this is my x-axis. This is starting to look like the equation of a straight line, right? Y equals mx plus b. So what you would do experimentally is get a bunch of data points, okay? So what you measure the rate of a reaction at a certain temperature. Okay, so I know the K at a certain T, and I repeat this over and over and over and over and over again. And I do this for a series of temperatures, and I get a series of rates. And instead of plotting the actual rate constants versus temperature, I plot the natural log of this rate constant versus the reciprocal of the temperature, right, 1 over T. So remember, if 1 over T is really small, like over here, it means that the temperature is very high. And so the rate is going to be pretty high, because usually at higher temperatures, reactions happen faster and faster. And then as I go to higher and higher temperatures, the rate gets smaller and smaller, right? So higher temperature is this way, and higher rate is this way. So I get a bunch of points. And then what you would do is fit this to a straight line, doing something called a linear regression. And the slope of the line, the slope over here, is minus the activation energy over R. So if I can measure what the slope of this line is, then I can tell you what the activation energy is, because I know the numerical value for R is about 8.314 joules per mole Kelvin. So once I get the slope, it's pretty easy to solve for the activation energy of the reaction.